Hi, everybody. Welcome to Physics C. My name's Angela Jensvold, and today we're going to review the work-energy theorem. Here's your warm-up. I'll give you 1 minute for this. Okay, I hope you drew a sketch. So you have a disk of mass m, and it's sliding with velocity v, and then it bounces back. We don't know what the speed is. We'll call it v final. And they said that the final kinetic energy is 1/4 the initial kinetic energy. So if you know the equation for kinetic energy, 1/2 mv squared, the final velocity is vf, we're just calling it vf, and the initial velocity they gave us is v. Okay, so if you look at this, the masses cancel, right? And actually the 1/2s cancel, and you get v final is v/2, okay? Okay, so today we're going to do 3 learning objectives, and here are the main ideas. You have the definition of work. You have the equation for kinetic energy, which we just used, 1/2 mv squared, and then you have the work energy theorem, and that's really important. So the overarching idea, we're talking about work and energy, right? So what is work? Work is a transfer of energy into or out of a system. So it's really important to understand what the concept of work is. It's not just an equation, F d cosine theta. So if somebody asks you what is work, don't say F d cosine theta. That's just an equation, okay, without really thinking about it. It's a transfer of energy into or out of a system. Okay, we're going to talk today about work done by friction. That is not calculable, okay? We're going to talk about that, and we're going to talk about why it's not calculable. The next point is very important. The work energy theorem can only be used when the object can be modeled as a point particle, okay? Meaning, what is a point particle? It means it's non-deformable, doesn't get squished or deformed, and not having the capacity for internal energy. So if you have an object and it has a capacity for internal energy, you should not be using the work energy theorem. Okay, so the work energy theorem, it's kind of like, think about kinematic equations. You know those 3 big kinematic equations? Can you use them all the time, everywhere? No, I hope you know that you can only use those equations for constant acceleration. It's the same thing here, okay? The work energy theorem is only for point particles, okay? That are non-deformable. Now, we have this equation here, definition of work, but what if you had a constant force? You don't need to integrate. You can just use F d cosine theta. But then the important thing is to know, what is D? D is the displacement of the point of application of the force. Okay, what the heck does that mean? So I have a folder. Can you guys see this? I have a folder, and then I have a book on my folder. So my finger is going to push the book. Okay, so the work done is whatever force I'm exerting. Let me try to do a horizontal force to make life easy. Okay, where is the point of application of the force? It's right where my fingertip touches the book. Okay, so the displacement D is how far my fingertip moves. The interface between my fingertip and the book moves. Now, in this case, the displacement of the point of application of the force is the same as the displacement of the object. So I know that when you guys calculate work, you often use D as the displacement of the object. That's because, just like in this case, the displacement of the object is the same as the displacement of the point of application of the force. Okay, so that's so important. Okay, I hope you guys will keep all of this in mind as we go forward. Okay, we're going to try this free response. Give you 2 minutes, but I'm going to change C to change in kinetic energy. Okay, go ahead. Okay, how'd you guys do? I think the first 3 questions are pretty straightforward, but then C and D are where you know, it requires a lot of thought. So let's start with A, determine the speed of the box. So we know velocity is the derivative of the position function, and speed is the magnitude of that. So it'd be 1.5 t squared plus 2, and they want the speed at 0 seconds. So plug in 0 and you get 2 meters per second. No problem. Part B, get the kinetic energy of the box as a function of time. So we're trying to get an expression. So kinetic energy is 1/2 mv squared, right? Our mass is 100. Half of that is 50. So I'm going to say 50 times 1.5 t squared plus 2 squared. There's our kinetic energy function. No problem. The net force acting on the box. Okay, so that is sum of forces, which is equal to mass times acceleration. Acceleration is the derivative of the velocity function. So let's take our mass, 100 kilograms, multiplied by the derivative of the velocity function, 3t, and you get 300t. There's your expression for the sum of forces at any time. Okay. Now, part C, we want to find the change in kinetic energy, and I just want to mention why I changed it. So you shouldn't use the work energy theorem to answer this question, because like we said, even if I go to the course and exam description of AP Physics C Mechanics, this is a document that's put out by the College Board and it's accessible online to everybody. Over here it says the work energy theorem can be used when an object or system can be modeled as a point-like particle, like we said before, non-deformable, not having the capacity for internal energy, right? Well, that box in the problem If you drag a box across a table or even my book across a folder, its temperature goes up. It gets warmer. Well, temperature is average kinetic energy of all the little particles that make up the book. I mean, if those little particles gained energy, where did that energy come from, right? That's called internal energy. Sometimes people call it thermal energy, but it's basically internal energy, okay? So it had to come from somewhere, right? So you can't use work energy on an object that if you have friction, because what's happening when you have friction? Let me see if I can show you. If you can see, I have shoe shine brushes here, okay? And what I'm gonna do is I'm gonna drag the light colored brush, the top brush, across the bottom brush. I'm gonna keep the bottom brush stationary. See that? Now there's two forces acting on the top brush. One of the forces is my hand. I'll pull horizontally to make it easier. Okay, do you see that the point of application of the force is where my fingertips are contacting the brush, right? If you compare the displacement of the brush to the displacement of the point of application of the force, it's the same, okay? But there's another force acting on the top brush, the bottom brush, and it's pulling the top brush this way, right? So I'm doing positive work, correct? Because my force is in the same direction as the displacement of the object, which is the same as the displacement of the point of application of the force. Okay, but the bottom brush is doing negative work. Could we calculate that? How much negative work is it doing? Okay, take a look very closely and watch what happens when I drag the top brush across the bottom brush. So my hand is doing positive work. The brush is doing negative work, but look closely. As the brush and my hand moved to the left, I think that's your left, the brushes bend. Can you see the brushes bending? That means that the force that the bottom brush exerts on the top brush moves over a shorter distance than the hand moves. Okay, so the point of application of my hand's force is the same as the displacement of the brush, but the point of application of the bottom brush's force is not the same as the displacement of the top brush, okay? So even if the force of the brush is the same magnitude as the force of my hand, the brush does less work because the point of application of the brush's force moves over a shorter distance. So that means the total work done on the brush is not 0 joules, it's some positive amount. Hold on now, if this brush moves at constant velocity, but I'm telling you that the total work was positive, why is it not gaining speed? If the net work done is positive, shouldn't it gain speed? No, because that extra energy went into the internal energy of the brush. The temperature of the brush is increasing, okay? So let me show you a diagram. The whole brush thing, that's just an analogy for friction, okay? You can't see it, but when I have my folder and my book, okay, and I push it, there's a lot more going on than meets the eye. Really what's happening is the bottom surface of my book and the top surface of my folder are really bumpy, and you can think of them as having like bristles, okay? And they get stuck and they spot weld, and then they break loose, and then a different spot on the notebook and the folder gets stuck. And that happens over and over and over. So just look at this diagram here, okay? So I've got my book and I've got my folder, all right? What is this here? This is like where the bristles are touching. That is the point of application of the force, right? Now look at the bottom diagram. my book moved a distance d, and the point of application of the force only moved a distance d over 2, because if these were the bristles, this is like the top brush, the body of it, and this is the bristle that's connected, okay? It would move a certain distance, but do you see how my fingertips did not move the same distance as the top of the brush? Okay. I wish I could zoom in. I was able to zoom in to the brushes with my special effects that I've got here. I don't quite have the technology to zoom in enough so you can see the little bristles on my notebook and my folder, but that's what's going on. So work is FD cosine theta, as we said before. But what is D? It's the displacement of the point of application of the force. How can we find that? Because it's very complicated. The friction force is spread out over, just like with the bristles, you had so many bristles. They were all moving at different, rates, right? They all got stuck at different points. So the friction force is spread out over the entire contact area of a surface that's sliding my notebook and my folder, for example. So the force is not localized at a point like it is with my finger force. My finger force, that's where the force is exerted. But for friction, it's spread out over the whole area of my book. So because the magnitudes of the friction forces at various points are constantly changing as you get individual point spot welding and then releasing, the surface of the book deforms locally, just in different regions of the book. And so the point of application of the friction force is not at all the same as the displacement of the book. So the displacement of the point of application of the force is not calculable. Therefore, the work done by friction is not calculable. So we cannot calculate work done by friction. That's my point. That's my point. Let's go back. Oh, okay. We're back here, and we're trying to get the change in kinetic energy, right? Okay, I just wanted to tell you why I changed the question. We can easily get the change in kinetic energy. Okay, now, you might ask, how are we going to calculate the energy that was transferred into internal energy? I thought about deriving it for you, but then I realized nobody cares but me. So I'll just give you the end result. Here is how you could do it. The work done by other forces minus, oh, do you guys realize I'm talking about kinetic friction? All my examples, we were sliding, right? So I'm talking about kinetic friction. Kinetic friction times distance equals the change in kinetic energy. We can use this expression. What is that second term? What is that second term? Well, what's most important is that you know what it is not. It is not work. Not work. Why isn't it work? Because you're taking the friction force and you're not multiplying it by the displacement of the point of application of that force, which is the definition of work. So you could say it's the amount of energy that is transferred from mechanical energy into internal energy. Do you guys know that mechanical energy is kinetic plus potential? Okay, so you have this macroscopic change in kinetic energy. I'm going to do positive work, right? What is work? It's a transfer of energy into or out of a system. I'm transferring energy into this system. My system is the notebook, okay? All right, so I'm doing positive work on this system, and then there is some energy that is transferred from, some of my energy goes into the macroscopic kinetic energy of the notebook, and then some of the energy goes into a microscopic kinetic energy of the particles that make up the notebook. That's internal energy. Okay, so that's sort of a little bit of an accounting. All right, so we'll use this expression, okay? Let's use that. And then we'll go back and solve this. Okay, so we want to get the change in kinetic energy. So you want kinetic energy at 2 seconds minus the kinetic energy at 1 second. That's a 1. Okay. At 2 seconds, oh, we erased our answer. The heck was our, oh, was it 300 T? Or was that, hang on, I wrote it down earlier. I don't really feel like doing it from scratch. Okay, it was 50. I guess it's not that hard. 1/2 m, 50 times 1.5 t squared plus 2 minus 50 times 4. Okay, you guys, this is 1/2 m. I don't want to lose you, but that's 1/2 m, and that's v at 0 squared. Are you with me? I hope I didn't lose you. Anyway, if you plug 2 seconds in here, and you use our expression, we calculated it earlier, the kinetic energy at 0, so we already did that, or the speed at 0. You end up with change in kinetic energy is 3,000 joules. That's what I got earlier. Okay, so that's how much the kinetic energy changed, and it's positive, so that means it increased. Okay, now here's a really good question. Indicate whether the work done on the box by the student would be greater than, less than, or equal to your answer in C. Okay, in order to do this, I try to organize my thoughts because it's too much going on at once. I draw an energy bar chart. So I say initial, work, and then final. So I divide it up. Okay, before anything happened, this box was just sitting there, and we'll say its initial energy is 0, okay? Then this student came in and did positive work. Why did the student do positive work? Because their force was in the same direction as the point of application of the force. By the way, this is the point of application of the force. Okay, that's the, all right, where did that energy go? Some of it went into kinetic energy of the box, and some of it went into internal energy. I feel like when you write out the bar chart, now we can answer D very easily. The work done on the box, if we color it in, is more than the change in kinetic energy. It started off with 0, so the change in kinetic energy is just the amount that it had in the end. So the answer is greater than, okay? Okay, try this one. This one should be easy. Okay, so let's draw a sketch. You have a ball and a string. It's going in a circle, and the force is string on ball. Okay, so where is the point of application of the force? Right here. Okay, if you want work, it's F D cosine theta. D cosine theta is the displacement. It's the component of the displacement that's parallel to the force. The force is toward the center of the circle. How much does the point of application of the force get displaced toward the center of the circle? It doesn't. It doesn't. So the work done by the tension force is 0. Okay, let's try another free response. Okay, so first you start with a force diagram, of course. So we have force of the earth on the compartment, and then we have normal of the track on the compartment. Hope you guys got that. And then it says, get the centripetal force. Do you guys remember what centripetal force is from last week? I hope you remember. It's just the sum of the forces in the radial direction. That's all centripetal force is, okay? And it also says don't add anything to your figure in part A. So let's go back up to the original diagram and we'll draw force of the earth on the compartment, normal of the ramp on the compartment, and then we want to draw components. So we'll draw components here. Now look, if this angle is theta, this angle is also theta. So the radial component would be mg sine theta, okay? So now we can sum the forces in the radial direction. Toward the center is normal of the ramp on the cart minus mg sine theta, okay? Okay, we're not done. Why don't you guys finish it up? Okay, so you want to get the speed of the compartment at D, right? So there's no friction from A to D. So let's just use the same expression we used earlier. So work done by other forces minus kinetic friction times D equals delta K. Okay, well, there is no friction along this section, so this will go to 0. So the work done by the other forces is going to be the work done by the Earth, right? The force of gravity. So we would do mg, and then you want the displacement that's parallel to the force, and that would be 3 force r plus r, and that's equal to 1/2 mv squared, right? V at d squared. Well, it looks like the masses are going to cancel. And now we can get an expression for velocity at d. So that would be, I was going to multiply by 2, so 6 force. You know what? I don't know why, but I really want to cancel this 2 and make it a 2. I hope that's okay with you. All right. So you get the square root of, oh, I can't do that. I'm doing illegal maneuvers. Wow. Okay, let me just add, you know what I'm gonna do? Add a step. I'm trying to go too fast. All right, so the right-hand side would be G times 7/4 R, right? And the left-hand side is 1/2 VD squared. Okay, so VD would be the square root of, now I can cancel one of these. Is that okay with you guys? 7/2 GR? Yeah? Okay, so I'm going to write that here. VD equals the square root of 7/2 GR. Okay, so we've got that. And then the next question is to get the coefficient of static friction. When the block goes from D to E, it just completely stops when it gets to E. So let's do that using the same equation, right? Work done by other forces minus kinetic friction times D is equal to change in kinetic energy. Well, there are no other forces besides friction, so we'll just eliminate that. And we have negative mu normal of the ground on the compartment times D equals 0 minus 1/2 mv squared. Okay, so now what is the normal? Let's just draw the block here. And you've got normal of the, I called it ground, check on the compartment. And then we have force of the earth on the compartment. Okay. I know you want to just put normal as mg. I know you want to do that, but it's really important that you draw a force diagram to understand what the value of the normal force. Look at this force diagram. You know it's not accelerating. You know the compartment is not accelerating in the vertical direction, right? So that means the normal force must equal the Earth's force. So in this case, normal is mg, but I strongly urge you to draw a force diagram every time just to make sure. So minus mu mg, what is d? D, it says, is 3r. The original speed is the velocity at d, right? Okay, so equals minus 1/2 m. What's VD squared? 7/2 GR. Okay, well, we can cancel m. We can cancel r. Oh, we can cancel g. This is nice. It's kind of fun. Oh, negatives cancels. This is like a big party for me. Okay, so mu is 7 over 3 times 4 is 12. What is that? I think I wrote it down earlier. 0.583. 0.583. So mu, where are my units? Am I getting sloppy? Is that what's happening here? Mu doesn't have units, right? Because it's a ratio of forces. So 0.583. All right, so now it says to write a differential equation. So it's not friction anymore, it's a drag force. And we're supposed to write a differential equation for the passenger compartment. It sounds so intimidating, differential equation. How will we ever do it? So acceleration is sum of forces over mass, right? You know that. That's Newton's second law. Okay. What are the forces? Negative kV. And what is acceleration? It's the derivative of velocity. Boom, we've got our differential equation. That was not hard. That was really not hard. It sounds hard, but it's not hard. It's deceiving, right? Because if I asked you to use the work energy theorem, you'd be like, oh, great, no problem. No, that is hard. That is hard. You have to make sure it's a point-like object, non-deformable, doesn't have the capacity for internal energy. That's something that seems easy, but is difficult. This sound, you could impress all your friends and say, I just wrote a differential equation. We all know your secret and we'll keep it. It's safe with us. Solve the, okay, now this one's a little bit harder, solving the differential equation. First, we got to separate the variables. I'm going to put all the v's on the left, okay? dv over v equals negative k over m dt. And then what are we going to do? We're going to integrate. We're going to integrate from v naught to v and from, can I just put this out front? 0 to t. Those are constants, right? So I can just put them out front. All right, so on the left, you have ln v from v naught to v. And on the right, you have negative k over m t, because it's minus 0 when you plug in the lower limit. Okay, so then you get ln of v over v naught equals negative k over mt. Raise both sides to the e, and you get v over v naught equals e to the negative k over mt. It's a little messy. So v is v naught e to the minus k over mt. I hope I did that right. Okay. All right, and then it says to sketch a graph of the acceleration. Well, shoot, we only have velocity. So what are we going to do? We are going to differentiate the velocity to get the acceleration. So acceleration is dv dt. So let's differentiate this function. Piece of cake, negative k v naught over m e to the minus k over mt. And if you sketch that, if you plug in 0, you would get, it says magnitude, right? We ignore the negative, okay? Don't worry about it. K v naught over m, and then it exponentially decayed. Uh-oh, I shouldn't have. Well, you guys, I'm gonna have to redo it because it touched the axis. I gotta be a little more careful. It never actually reaches 0, right? It approaches 0. I was rushing. Not bad, not bad. Try this experimental one. All right, so if you read the question, it says the motion sensor is used to measure the position and speed of the cart. Force sensor is used to measure the force the spring exerts on the cart. So which of these questions can be tested using the equipment? The speed of the cart as it reaches the spring, we can definitely measure that, is directly proportional to the cart's initial distance from the spring. No, 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 no. Look at the motion sensor. It's measuring the distance from the motion sensor to the cart, not from the cart to the spring. It can't see past the cart. Okay, so that's no. Speed of the cart, we can measure that. As it reaches the spring is directly proportional to the average force the students exert on the cart. The students are pushing this way. I'm going to try to draw a hand. Okay. The students are pushing from the left, and this force sensor measures the force from the right. So this is no good. Same thing for C, force students exert on the cart. The work done, we can get the work done by the spring because we can measure with the motion sensor, we can measure the displacement of the cart once it hits the spring. Initial kinetic energy, the motion sensor will also measure speed. So the answer is D. I hope that's what you chose. Okay, another experimental question. Okay, you know you're going to have an experimental design question this year, right? This is a really common question, and it's certainly fair game for this year because you could type this out very easily. You've got your function f equals ax squared, right? And you want to make a line, so you just do y equals mx plus b. Well, in this case, we don't have a vertical intercept, that's 0, but our vertical variable should be force. Our horizontal variable should be x squared because we're trying to get our slope to be a, so that means you would graph force versus x squared. And so in part B, you need to add a column to the table, x squared in meters squared, and they'll probably give you easier numbers because this, a calculator is not required this year. So these numbers are, you could do them in your head, but take too much time and it might cause a little bit of stress. So those are the numbers I got. I hope that's what you guys got. Okay, now see if you can finish it up. Okay, guys, we're running out of time, so I'm cutting you off. I made the graph while you were working. It says using your graph, calculate A. So what you need to remember is that whenever you use your graph, okay, to calculate the slope, you've got to use 2 points on the line. Don't use data points. Use 2 points. I'm still on my line. On the line. So what would I choose? I don't have 2 really amazing points. Ooh, can I fudge this one? I'm going to fudge that one a little bit because we're running out of time. So the slope is A. So you would do 100 minus 50 over 0.055 minus 0.03. And whatever you get for that is A. Okay, we don't have time to calculate it right now. Then you want to calculate the work done in compressing the spring. That's the integral of f of x dx, right? So you want to compress it from 0 to 0.1. And the equation for that force was ax squared, right? Oh my goodness, I don't know what happened there. Okay, ax squared dx. So that would be 1/3 ax cubed from 0 to 0.1. And so you would plug whatever value got from a in here, and then 0.1. So it would be 1/3 of a times 0.1 cubed. That would be the work done, okay? And then the speed of the cart, just before it strikes the spring, you would do work equals, work done by other forces minus kinetic friction times D equals change in kinetic energy. So you can use this expression. I don't believe there's any friction, so you could just get rid of that second term, right? And then you could calculate it that way. And then kinetic energy, change in kinetic energy is 1/2 m v final squared, which was 0 in this case, minus 1/2 mv initial squared, and that's what you're looking for is v initial. We don't have time to solve it, but that's how you would set it up, okay? Okay, I'm going to give you this experimental question for you guys to do for homework. Do it with your teachers, do it with your friends, just do it virtually. Okay, this is a nice opportunity for you guys to get together and chat about physics. Physics brings people together virtually. Okay, everybody stay home, stay safe, and I'll see you soon.